In today's lecture, we'll see applications of exponential and logarithmic equations. So we'll see how we can actually use logarithms in these equations in order to solve for some variables. And we'll see two examples. The first one involving doubling an investment that we make at the bank, and the second one involving retail sales at a store. So let's get started. Let's say you invest $500 at an annual interest rate of 6.75% compounded continuously. How long will it take for your money to double? This is a good question, and to solve it, we need to remember our continuous compounding formula, which is a very nice and clean formula. A is equal to P times E to the RT. Here, P is the initial investment, A is how much money we want after some time period, R is our annual interest rate, and T is time. Since we're trying to solve for how long it will take, then T is the variable we solve for, and all the other numbers should be given, and they are. Our initial investment is $500. Our rate is 6.75%, which as a decimal is 0.0675. And if we want our $500 to double, this means that we want A to be 1,000. All right, now that we have this plugged in, we'll once again get E by itself and then cancel it out. So step one is divide by 500 on both sides. And then we get 2 is equal to E to the power 0.0675 times T. Now to cancel out our exponential on one side, we take the natural log of both. So we get the natural log of 2 is equal to the natural log of E to the power 0.0675t. And the right-hand side cancels out. So we're left with the natural log of 2 is equal to 0.0675 times t. And finally, we solve for t by dividing the natural log of 2 by this decimal 0.0675, which gives us that t is about 10.27 years. So at a rate of 6.75% compounded continuously, it takes a little over 10 years for our money to double. Finding out how long it takes our money to double is a very important number to know. There's actually a shorthand called the Rule of 72. An investment with any kind of compound interest, be that compounded annually or continuously, will double in value around 72 divided by the APR, years. So for this one, our APR, annual percentage rate, is 6.75. So the rule of 72 tells us that our money should double in 72 divided by 6.75 years, which is actually equal to 10.6 repeating years, which is pretty close to the number we worked it out to be. All right, let's move on to the next example here. We're looking at retail sales, and we see that our sales are modeled by an equation. Y is equal to negative 566 plus 244.7 times the natural log of t, where t is allowed to range between 12 and 20. We let y equals 1 represent $1 billion, and t is in years, where t is equal to 12, corresponds to the year 2002. And using these small numbers allows us to condense this equation so that we don't have to deal with numbers that are billions large. With these constraints, let's find what year our sales will reach 141 billion if they keep following the same equation. So remember, y is equal to sales in billions. So we set this up. We let y equal 141. And now that we have that in place, we simply fill in the other side, which is negative 566 plus 244.7 times the natural log of t. At this point, all we need to do is simplify by adding 566 to the other side, so that we have 707 is equal to 244.7 times the natural log of t. Then we divide by 244.7, and we get that 707 divided by 244.7 is equal to the natural log of t. And then in order to cancel out our logarithm, we add an e on both sides of the equation. So we have e to the power natural log of t is equal to e to the power 707 divided by 244.7, which is actually very close to the number 18. On the left-hand side, e to the power ln of t cancels out, and we're just left with t. And the right-hand side, we said, is about 18 years. So if 12 is equal to 2002, then 18 is equal to the year 2008, since it's 6 bigger. And we can say that in 2008, our retail sales should reach 141 billion. We can pinpoint time by measuring these sales and then canceling out the natural log with our exponents. So let's do one more example just to refresh ourselves on these properties of logarithms. And at this point, I would encourage you to pause the video and try to solve this one on your own. And when you have an answer, go ahead and unpause it and we'll get to work. All right. Now remember that in order to use our inverse property, or one-to-one property, we need to condense the left-hand side to be one logarithm. So we take the plus on the outside, and we condense this down to be multiplication on the outside, or on the inside. So this becomes log of 5x times x minus 1 is equal to 2. The addition on the outside became multiplication on the inside. All right. If we FOIL out 5x times x minus 1, we'll get 5x squared minus 5x is equal to 2. And now we want to cancel out our log. So remember, if there's no number on the log, it's base 10. So in order to cancel it out, we add a 10 as an exponent on both sides. So we have 10 to the power log base 5x squared minus 5x is equal to 10 to the power 2. The left-hand side simply cancels out, and we get 5x squared minus 5x, and the right-hand side becomes 10 squared, which is 100. Now we have a polynomial, and our goal should be to move everything to one side, factor it, and then find the answers. All right, so we have 5x squared minus 5x minus 100 is equal to 0. And notice that everything has a multiple of 5 in it. So I can simplify this down and make this 5 times x squared minus x minus 20 is equal to 0. And this is much easier to factor. Two numbers that multiply to be negative 20 and add to be negative 1 are negative 5 and positive 4. So this is 5 times x minus 5 times x plus 4 is equal to 0. And we have our answer now. Either x is equal to 5 or x is equal to negative 4. But we need to be careful here. Remember that in a logarithm, we're not allowed to plug any negative numbers into it, otherwise we'll have a problem with the domain. So if we take negative 4 and we plug it into our original equation, we get log of negative 20 plus log of negative 5 is equal to 2. And neither one of these are defined. These are both not defined. So this means x equals negative 4 is not in the domain. So when we get a negative number, we need to plug it back into the equation to see whether or not that'll actually be defined. So it turns out the only time that log of 5x plus log of x minus 1 equals 2 is exactly when x equals 5, and we have our answer.